Welcome, this is Dr. G, and this is an introduction video to reaction kinetics, which focuses on all the different aspects of chemical reactions, with particular emphasis on the rates of those chemical reactions. In this video, we'll first take a look at how chemical reactions actually occur by looking at the collision theory, and also focusing on the different relationships between the energies involved in chemical reactions, mainly the kinetic and potential energy, as well as introducing a term called the activation energy. You got this. Come on, let's go. The study of chemical reactions falls under two main branches: reaction kinetics and thermodynamics. For reaction kinetics, it focuses on the pathway from the reactants to the products. In other words, it cares about what actually happens in a reaction. On the other hand, thermodynamics is dealing with the energetics of both the products and the reactants. In other words, it cares more about what theoretically can or should happen in a chemical reaction. In reaction kinetics, there is a strong emphasis placed on the conceptual understanding of, as well as the calculations involving the rates of different pathways of chemical reactions. The fundamental concept within reaction kinetics lies in the collision theory, which states that in order for a chemical reaction to occur, there must first be a successful collision between particles. In other words, if there's no collision, then there's no chemical reaction. These collisions can occur because of a different theory we know as the kinetic molecular theory, which states that all matter is made up of tiny particles that are always in constant motion, therefore they will have a chance at colliding with each other. Let's go back to the definition of collision theory and focus in on the two words successful collision. What determines whether or not a collision is successful? As it turns out, there are two requirements for a successful collision. The first one is the particles must collide with sufficient speed. The second requirement is the particles must collide with the correct geometry. Now, instead of saying sufficient speed, we can also say sufficient kinetic energy. And that's because, recall, the kinetic energy equation is equal to 1/2 mv squared. So essentially, the kinetic energy is proportional to velocity, which is pretty much the same thing as speed in our case. Due to the conservation of energy, if you have sufficient kinetic energy, you should also have sufficient potential energy because the two energies can convert from one form to the other. We'll take a closer look at the relationship between the kinetic energy, marked in red as EK, as well as the potential energy in purple, or EP, in this example. Let's start with two particles that are very far away, but they are on a collision course destined to collide with each other. Now, because they're very far away, and due to the kinetic molecular theory, they're going to be moving, which means they're going to have maximum kinetic energy, or EK, and minimum potential energy. As these two particles move closer together, the electrons on their outer orbitals are going to repulse, and therefore slow down the two particles. And because they slow down, they lose speed, or in other words, their kinetic energy drops. But because of the conservation of energy, if the kinetic energy drops, that means the potential or stored energy rises by the same amount. At the moment of collision, there is maximum potential energy because in that brief moment, they are both not moving. And because they're not moving, all the energy that once was the kinetic energy is now in the form of potential energy, and we have almost no kinetic energy left. Also, the collision of the reactants results in a very high energy and unstable intermediate compound known as activated complex. After the collision, now we have products. And these products also have electrons on their valence shells, and these electrons will repel, causing these products to move away from each other. And that is going to cause them to pick up speed or kinetic energy. And of course, that will come at a cost of your potential energy. Finally, as our products are now infinitely far away from each other, they now have maximum kinetic energy again with minimum potential energy. So now we know that during a collision of a chemical reaction, all the kinetic energy that a particle had as it was moving towards the other particle gets converted to potential energy at the moment of collision. To have sufficient kinetic energy means that you must possess enough kinetic energy so that you may have a successful collision. Well, what is enough? Enough means you must meet the minimum required kinetic energy or the threshold kinetic energy, and there is a term for that. That is called the activation energy. The activation energy is the minimum kinetic energy required for successful collision. That is its definition. Now, one note here, we did say that whatever kinetic energy you had is converted into potential energy at the moment of collision, which means if you have sufficient kinetic energy, you should also have sufficient potential energy. If you didn't have sufficient kinetic energy for the collision, then there's no way you would have sufficient potential energy for the collision as well. So although by definition, the activation energy is the minimum kinetic energy due to the conservation of energy, it also represents the minimum potential energy. As a summary, the collision theory states that in order for a chemical reaction to occur, there must be a successful collision, and to have a successful collision, there are two requirements. First and foremost, these two particles must collide at the proper geometry. And the second requirement states that the particles must have a sufficient kinetic energy, meaning that their kinetic energy must be higher than the activation energy, or we can also say that their potential energy must be also higher than the activation energy, because again, all the kinetic energy that they have will be converted to potential energy at the moment of collision anyway. And that is it for this video. Hopefully you have a better understanding of what collision theory is now, as well as how the different energies play a role together in a chemical reaction. If you enjoyed this video, remember to hit the like button, and if you really enjoyed this video, feel free to subscribe. It will help my channel grow. If you have any questions or comments or any topic requests, feel free to put it down in the comment section down below.